again. So I got actually a great question during the quiz, or with somebody who was done with it, like about the reallocate. And he's like, and you said, I thought when you set one equal to the other, you get both of these, to alias the same variable. So I just want to draw the diagram of what goes on here, just because we didn't see it earlier. Okay. So our first line of code was basically, so we have this array over here. That's our, I'll draw it over here. So this is our data array currently, right? It's nice and full, completely full. So now we need to reallocate it. So I'll say that, right? So data, right? It points to this array somewhere in memory. Okay. So what we're doing is that we're saying something that our first line of code is old, new generic array, old data is equal to data. And what that does is that says, let's take the memory location on the right and store it in the left. So we're going to take the memory location of this array and store it in old data. So that means that old data also points to this. Okay? So these now point to the same array, right? And now I double the capacity, and the next line says, let's create a new array that's twice the size. Okay? So, and we're going to store the memory location of that in data. So we create a new memory. So let's go ahead and evaluate the right-hand side first. We evaluate that. It's a new array, twice the size. I know it's not this, I guess not to scale, but because I'm terrible at drawing. But we'll go ahead and say, take this data. Now we take the memory location of this array, store it in data, and so now data points to this. Okay? And now we simply transfer everything from old data over into this one. And once we're done with this code, the reallocate code, old data was a local variable, so once we're done with this method, old data goes away. So what happens to this array? It gets garbage collected, which if you haven't learned about that yet, we're going to learn about that when we get into linked lists in a bit of detail, just to make sure you understand how that works, because it's essential to understanding why you don't have to, why Java is slightly easier than C. Okay? Now, again, the way, and in case you didn't learn this in 1068, the way arrays work with memory location is that when we say the memory location of an array, it gives you the memory location of the first item in the array. So the way Java is able to quickly figure out what item you want in an array is that there's an equation. It simply says, okay, your array, right? So the memory location of the memory location of a specific thing in the array is the memory location of the actual thing in the array plus the index that you just asked me for, right? So times, the size, I'll just put size of thing over here, which is the size of whatever you store, of whatever happens to be in the array. So the memory location is byte number, let's call it 100, okay, of the array. So we're stored at memory location 100. So if we're looking for index 0, that means that this goes to, that this index 0, this becomes 0. So it says, let's look at, let's go ahead and look at memory location 100 for the first item, which is 4 bytes long if we're storing integers, okay? So say again, we're dealing with the same array of integers, okay? Memory location stores at 100. Say I'm looking for index 5. So we'll look at index 5 times the size of the thing in the array, which is an integer, that's 4 bytes. So 5 times 4 is 20. So it knows to look at memory location 120. Well, it'd be something else in hexadecimal, but you get the picture. And that's how basically, so that's why looking up stuff in an array is so quick. It's able to do just this calculation really quickly to do this. And it's the same thing for two-dimensional arrays. It just adds in more offsets. So anyway, that's how reallocate is working there. So now I built this array list. It wasn't a Java list, but it was a close enough facsimile. The other thing to note about the array, about the way Java lists, and I didn't mention this in the evening class, is that the Java lists also have a they have a second constructor. Actually, they have a couple of more constructors, but the one to note is a constructor that takes in an int capacity, which allows the user at runtime to set the initial capacity. So if you do know how big your array list is going to be, this is pretty nice because you can just say, hey, array list, be exactly this big, because you'll never need to double pass this size. So, and what you'll do is just simply set the same thing. Size is equal to 0. And instead of doing initial capacity, we just put in capacity and capacity, right? That's all we do. So that's the only difference. So that's, but by default, Java's initial capacity also starts at 10, if I recall correctly. Yes.
Is that just for like name constraints?
Yeah, that's just if you want to be a bit more efficient with your memory. Okay, because remember, one of the big disadvantages of using an array list over an array is that, we might need only, it might double and you end up using maybe only half the space you actually need, half the space that's actually allocated to you in that. Okay, so now your homework this week are going to be a bunch of exercises. And they shouldn't be too scary to you because they're stuff you should have done with arrays, only now you're going to do them with array lists. Nothing too scary there. So let's look at a basic example and see how we can use these. So array list examples. So here we're going to actually work with the Java array list and then the array list I created here. We can use array lists in methods. So I'm going to go with one that I did last year. I'm going to change. So this was on the homework last year. I'm going to change it up slightly, but it's a very simple method which asks, given an array list which contains only integers, give me the sum of all the things in this list, right? That's not hard, right? Theoretically speaking, right? It's just, in fact, you probably wrote it as like a very basic exercise or possibly even as an exam question in 1068, right? It's not a particularly difficult problem, but it's good for getting us into the habit of using stuff again. Right now we're building up muscles for our thing, and that's kind of level of difficulty of stuff you should expect for the timed lab. It's nothing. So time lab isn't this week. It's going to be next week, it's going to be about as difficult. The individual problems on that lab should be about as difficult as this homework is going to be. So this will be good practice for the timed lab. So let's go ahead and say public static int sum. And we're going to take in an array list over here. Okay. And right now, I should use generics, but I'm going to not use them for right now because I'm going to, again, remind you why we want to use generics. And then I'm going to show you how easy it is to use generics in methods. Okay. So, and sums are very easy. It's like int sum a running sum is very easy, right? We just want to sum up all the things in this list. Int sum is equal to 0. Return the sum when we're done adding stuff to it. Okay. And now, for int I is equal to 0, right? Because we're going to start at index 0. I is less than, well, if list was an array, we would go .length, right? But we're an array list. Size. And, oh, that was nice. Eclipse automatically imported array list for me, I believe. And then, oh, it says E. It automatically added in this generic for me, but I don't need that yet. I++. Okay. And now, if we weren't using generics, we'd have two issues. The first is that basically for me to do sum plus equal, and remember, if this was an array, we'd be going, using the subscript notation, but here we have to use the get method instead. So get I. Now, the first thing is that while I'm returning an integer, it's an array list of anything right now. So I'd have to cast it. That's the first problem, okay, in order for this to work. And the second problem is, if I passed an array list that had strings in it, I could totally pass it into this method. Nothing would stop me from passing it into this method, right? Because this takes any array list that you want. And then it would crash as soon as it got to this whole thing. So what we can do is that we can actually add generics to the method parameters and tell Java we can take only array lists that hold a certain type. So here we can say we only want We only want array lists that hold integer, right? So now we don't have to do any casting. We know that this array list will only hold ints, which is nice. That's pretty nice and easy to use, right? Okay. So that's fairly straightforward. So you can basically so that's the first way we can use generics in static methods like this, right? So notice that, right, these are static methods. Over here, basically in instance methods, if we use generics, they were just simply the same that was attached to a class, right? But static methods, I might have a sum method for integers, and I might have a sum method for doubles, right? So, you know. All right, but let's say I'm going to write the whole contains method again, only as a static method, okay? Just not, and I know I hate redoing work, but let's go ahead and just do this simply because we can, it will basically show you the other way that generics can be used. So public Boolean contains, and this will look for, and I have and just in case this does get confusing, I have a very lengthy full-page write-up on your homework about how this works, or the proper way to do this. ArrayList, ArrayList of items. So ArrayList list, and I want to search this for some object in the list. Okay, right, so I want to do that. I want to search this, see if this contains some item, the whole, so assume it's not going to find the item, so that's my default value. Then for int I is equal to 0, I is less than, so I is less than list.size, I plus plus, if list.get, so if the item that I get at index I dot equals the item I'm searching for, return true. But mind you, it's still giving me that warning because it's saying, well, you've got an array list, you really should parameterize it, right? You really should make sure that everything, is, if it's the same type, you should say so. So one way I can do that is by putting in, I'm going to put T to distinguish it from E, and that's what a lot of times what's done in Java. And basically it's saying that basically this array list holds all these things of the same type, that type T. This array list has stuff of all the same type, denoted by type T. And this second item I'm passing in is also the same, of type T, right? These things are exactly the same, it's saying that this type of object the array list contains is the same over here. So that's a nice bit of useful information I could communicate. It's not really relevant for this problem, but say I'm doing some sorting problem. That's pretty, useful because if they weren't the same type, I wouldn't be able to sort them, okay? All right. And so the way is, so sorry, I skipped ahead. So it's still giving me an error saying it doesn't know what T is. So when we're doing methods that have this kind of generic operation, you have this weird thing you have to put in, and it's just right over here after the static. And you say basically, what we're saying now is that, first off, ignore this stuff over here. Okay, this is just another thing we can add to a method. And all it's saying is that public static, and this is optional. It says this method will take in a generic. It's only used for this method, okay? Only used for this method. So I could have a T in another method, just like I could have an X, two variables named X in two different methods, right? Public static T Boolean contains, so this method has a generic of type T in it. So all the T's in this are the same. So this array list holds T's and T.item. Now you only have to use this. So notice over here I said it was a list of integers over here, and this one it's T. You only have to use this weird notation if you don't know what type the generic's going to be. If you know it's an array list of something, you can just go ahead and say what that is, right? If it's an array, if you know it's going to be an array list of doubles, or an array list of integers, or an array list of strings, you can put that array list of strings right over here and just write it like any other method. If you don't know what it is, then you can put this over here. Now you might be going to yourself, why in the world is it like this? And the answer is that we can do some stuff, say if we're sorting things that are useful. We can, we'll get into this a bit later, I think, but not too much later, because I didn't go over this in the evening class, but you can do this. What? Comparable D sort. And so this is a sorting method. I didn't put in my return statement, sorry. So, all right. That's interesting. So let me just start out. Remember, what is the objective of sorting, right? Sorting was a problem you probably learned, right? And if you didn't learn it for some reason, it's pretty easy to understand. The objective of sorting is to put stuff in from the lowest, in order from the smallest value to the biggest value. Okay, not too scary to understand how that works. But things need to be able to be ordered. So comparable is an interface, right? And it just means it's a compare. And what it says is that it provides one method called compare to, and it just simply says we'll learn more about compare to when we do trees. But what it allows us to do is say basically that if it implements comparable, for instance, integer is comparable. If things are comparable, then we can put them in order. Okay, and so we're enforcing that basically this array list of stuff that we're trying to sort. We're saying that this type, which extends comparable, can be sorted. Does that make sense? It's saying that basically that this array list of stuff can be sorted. So we aren't just throwing scanners in here because scanners can't be sorted. We can't sort an array list of scanners. Scanners can't be put in order. They're not comparable. But we can put in an array list of integers. Now, you're not going to have to do this for this homework, but this is more of explaining why this feature exists. And I think there's an easier, a shorter way to do this, like extends comparable. So yeah, that is a shorter way to do it. But and again, I used to know, like when I first taught this class, I did like a couple weeks on like a week on generics and advanced use of generics and that kind of stuff. But I dropped that because it was a time constraint thing. And I used to know why you would want to use this as opposed to the other type, but now I can't remember. And if you really want to know, I'll look it up for you guys. But there's more right now. There's more than one way to skin a cat, which is rather morbid. I don't know why we'd want to do that. But the most you're going to have to do is this. Okay. So we can use array lists basically anywhere you want to use arrays, and we can do the same kind of operations with them we want to use arrays for. All right. So we've got about 25 minutes left, so we're going to go ahead and start on the next session of this, which is that we need to start talking about, let's see, what we can do with basically these array lists. Because we're going to learn linked lists next. And the question is, okay, if we have array lists and we have linked lists, why are we going to bother learning like two different types of lists, right? And the answer is because one is better than the other at certain types of things, okay? So right now, and so how do we know stuff is better? Well, some things are good at other things. So let's go ahead and talk about like the costs of writing a program. Okay, so writing a program and running it more has a cost associated with it. They use up some valuable resources, always. So first, what is the most valuable resource so first off, computers use up one specific resource that we almost always concern ourselves with, and it is the most valuable resource in the world. Why is it the most valuable resource in the world? Because this is a resource you cannot buy. Time. You cannot buy time. Time is the most valuable resource of all, because you cannot buy more of it. All the other resources that we might concern ourselves with, such as, what's another resource that a computer uses? Memory. And what's another one that you might be interested in if you've got one of these pocket things in your pocket? Power. Yeah, power. The processor basically ties into time, and space ties into memory as well. Yeah, power or energy is is valuable. Basically, making sure that our algorithms, they run as as cheaply as possible and use up the least amount of memory. You'd really hate it basically if your battery drained because it was continuously searching for Wi-Fi in a very inefficient manner. These algorithms improve over time. Okay, so time, memory, power, these are the kind of things that we care about when we write our algorithms. But we care about time most of all. I mean, it takes about if your web page takes more than 3 seconds to load, that's about when the user experience people say, hey, that's when our users start getting irritated, right? So we really need, to keep these things, down. Memory is also pretty important because, if you duplicate too much data, that's going to cost a lot of memory, which costs money on servers and stuff. And power is important if you're writing a mobile app. So you'd rather these things be as efficient as possible in terms of memory. Now, it's a bit harder to do because that's a lot of low-level stuff going on there. But if you make it run quicker, then ostensibly it's going to use less memory. If you make it use up, if you spend less time in high energy consumption, right, tying back the time there, then that's probably good. It's also very useful, not just for these little computers in our pockets, but basically for anything we need to deploy, like a sensor. In a lot of the research papers I had to read when I was going through graduate school, there's always about like wireless stuff and these ad hoc networks. They would always put in about energy cost and how energy cost is very important for if it's a battlefield kind of scenario where basically there is nowhere to plug in to power. So that's kind of so power is a very important thing. Memory is important, but because a lot of these computers come equipped with more than 4 gigs these days of RAM, memory is a bit less of a consideration. Time though, computers get faster and faster, but that doesn't necessarily mean that some problems become easier and easier. So we're going to learn about, so how many of you are in Math Concepts 2, right? So a lot of you, how many of you are learning about big O notation right now? Like right now, did it just start this week?
Yeah.
Well, guess what? It's a double whammy for you guys because we go over that. Now, fortunately for you guys, and those of you who are not in Math Concepts 2, we are taking a more layman's approach to this and a less mathematically strenuous approach to this, to big O notation and algorithmic efficiency. Instead, we aim to teach you what it feels like and kind of just do some quick and dirty evaluations of how long your algorithm takes to run. So I will ask you on your first exam to write some stuff, some basic algorithms that are similar to the ones I just did, right? On your actual first paper exam. And one of the questions on there will be so you just wrote this algorithm. How long, what is the big O notation of your algorithm that you just wrote? And we're going to concern ourselves with basically 3 notations, right, to begin with. We're going to learn about constant time, linear time, and quadratic time. So constant, linear, and quadratic. But I get ahead of myself. Okay? First, let's actually, before we step completely into the realm of the theoretical, let's go ahead and, ground ourselves in the real world and actually see that some stuff does take longer to run than other stuff, and that there is a kind of relationship we can say, it's not just a random amount of time it takes. There's actually a predictable amount of time that something can take. So, okay, so let's go ahead and start by writing a basic method. So first off, if we're going to time something, we need to figure out, how do we actually time things, which also means we actually have to figure out how time can be measured, which is actually really, really, really hard because So first things first, never, ever, ever mess with time yourself. Somebody else has already done it for you. Do not mess with time yourself. Do not make a library that tries to calculate dates. Do not try to make a memory that calculates the amount of seconds that have passed since an event. Do not try to, actually ever count, do not roll your own when it comes to time. It is hard because you have to account for leap seconds if you're just working with seconds. If you are working with converting calendars, you have to take into account that certain calendars have leap months. The Jewish calendar has a leap month, as opposed to a leap day that the Gregorian calendar has. And that's different than the Julian calendar, which was used, before it was fully adopted. And it wasn't fully adopted. The Gregorian calendar wasn't adopted by every civil government until late 1950s, I think, or something like that. It took a while. Yeah, so these governments do, so, it's great that we're all on the same timetable, but if we look at the Wikipedia page for George Washington, you'll note that it has 2 birthdays down for him, one under the Julian calendar and one under the Gregorian calendar, because, that date changed based on that. So right now what we're going to do is we're going to work we're going to let the computer's library handle that for us, and we're going to just be counting the number of seconds that have passed since 1970. That's literally how we track time.
So basically you're going to import time.
Yeah, but, it's actually built in. So what we're going to do is that we're going to use system and there's nanotime, which would count time in nanoseconds, but I'm just going to use the current time in milliseconds. Okay, so and if we want to time something, this gives us a rough estimate of how long it's going to take. So int start, long start, because this is a big number, is equal to system.current time in milliseconds. And if I want to find out basically how long some code takes, I do this line at the beginning, and then when my code is finished, I go end, and then I do system dot, I get the current time at the end, and then I can subtract the two. So system.out.println, I can say start, right? I can say when this starts, I can say when it ends. And this is going to actually be quite boring for the beginning because it's going to be really quick. It's we're probably going to end up with 0, right? So boom, boom, and my start. Right, takes less than a millisecond to execute both those commands, and so nothing too interesting happens there. Computers do stuff quick, okay? Which means that in order to see things actually happen in our computer, whatever I'm going to be testing in between here has to take up a decent amount of time. So. Which is why I'm going to work on really big stuff. So public static void create. So I'm going to show you what happens when we create array lists. So create array list test, and I'm just going to copy and paste some of this code over here. So all I'm going to do is I'm going to grab this, and I'm just going to slap this in here. Okay. So I want to test how long it takes to, first thing first, I'm going to build an array list. I'm just going to make an empty array list of default size. Array list is equal to new array list. Forgot to do the integer on the other side. I'll get back to that. That's fine. It's just going to be an array list of integers. Very boring array list, in fact. Array list of integers. Need to import the array list. That's fine. And what I'm going to do is that I actually need, in order for this to actually take a measurable amount of time, I have to add a lot of stuff here. So for int I is equal to 0, I is less than 10,000, 100,000, 1 million, 10 million, 100 million. Let's go with 100 million. So I++ list dot add I. What? You'll see. It's fine. It's going to take up. It's going to take a. The point is that we'll take an appropriate amount of time, and once there's going to be some speed bumps on here. Okay, and this is more to demonstrate. This one's a bit harder to execute because this one isn't going to be precisely linear. It's actually more of an. This one's a bit harder to analyze, but we'll get into that. This one. we'll get into an actual linear time operation in just a bit. But let's see. We're looking at, I called it create array list test. So it depends on how long this takes, of course, depends on your computer. Now, all computers can do the same thing other computers can do. It's just that some can do it faster because, advances in technology. So run this, and this should, it's adding this. And that took about 4 seconds to complete, okay? 4.2 seconds to complete, 4,000 milliseconds. If I run it again, right, it really just depends sometimes. Like, we're going to get some jitter in there. It'll take a bit longer or a bit shorter. Just depending on how long certain things take, okay? So that takes 4, milliseconds. And what's cool is that actually, I reduced the number of things I add to this list by a factor of 10. 10 times less. And if I reduce that further by a factor of 10, takes 10 times less. Okay, so there's kind of a linear relationship going on over here, right? Increasing it by 10, increasing the size of the list that I'm making increases the amount of time this takes by 10. Decreasing the size decreases it by a factor of 10. Okay, but now let's switch this up a bit because not everything is made equal. Rather than so here's what we're going to do. Rather than adding it to the end of the list, I'm going to add it to the beginning of the list. Each item is going to get added to the beginning of the list instead. So this is why I wasn't too worried about like any threading that might happen, because now I did hit the button. It is actually running over here. So I'm not going to bother waiting because I have a good idea of how long this is going to take. I'm going to reduce the size of the list by a factor of 100, and I'm going to run it. Again. Now it's running. Now it's running. Still running. Oh, wow. Still running. So the million items inserted into this list. All at index 0. I mean, I can hear the fans, just kind of just hissing along right over here on this machine. Do I need to give, let's go ahead and give it another, and I mean, this is a fairly good processor too. This is like the latest i7, processor. So let's go ahead and reduce this by another factor of 10. Okay, so that took, okay, too much. Increase it by a factor of 10. So, okay. So doing 100,000 items took, takes about 0.4 milliseconds. Sorry, 0.4 seconds. Now let's go ahead and run it again, factor of 10. And that's still running. So what's going on over here? Why is it so much more difficult to add it to the front rather than the back? Yes? That's exactly right, because I have to shift every single element in the front. Now, when it comes to remember, there's two operations that if we think about it, make sense that they're expensive when we are adding things to a list. The first thing is whenever a list fills up, it's expensive because then we have to create a new list, which isn't too expensive, but then we have to copy everything over from the first array to the second array. So that's an expensive operation, but that doesn't have to happen too much, okay? The other operation, though, is that basically if we're adding anywhere besides the end of the list, then we have to shift over a bunch of items. So if we're adding to the first item in the list, every time we add, we have to shift an item over. Now this first item, so the first test I ran where I was just adding to the end, that's an example of a linear time operation, an O of n time operation. If it takes n time units, if it's of n size, it's going to take n time units roughly, okay? Or or there's some linear relationship. Maybe if it's n size, it will take maybe 0.4 n time units, okay, or something like that. But the end result of that is that since that's a linear equation, if my input size is increased by a factor of 10, so if I multiply it by 10, finish there, then it will be multiplied then the amount of time it's going to take is multiplied by a factor of 10. On the other hand, with what we're dealing with over here, a quadratic time operation, which is what the continual adding to the front is. Not adding to the front once, but adding to the front again and again and again and again. That was a quadratic time relationship. We're basically saying for an input size, right, that was, and it takes n squares time. So input size n takes n squared time units, which means if I increase the size by 10 over here, the input size by 10, how much does the amount of time take increase? About 100, which is 10 squared. So it took 100 times longer to do this, or roughly 100 times longer, because again, because it's a rough relationship, which we'll get into. So these operations take time. Now we're going to learn throughout the semester other big O notation times, but right now we're going to focus on these three. The other ones we're going to learn are log of n. When we get into recursion, we're going to learn log of n. And when we get into doing sorting algorithms, we'll deal with n log n. And I'll talk a bit about like the really terrible times as well. We'll talk about factorial times and exponential time. But this is where like basically where the theoretical stuff really comes to bear. It's like, why do I need to know these things? Well, because the difference between taking a minute to add things and taking not taking forever to add things matters. And then knowing what data structure does matter. So let me go ahead and just switch this from being a list over here, from an array list to just a list over here. And I'm going to switch this to being a linked list. Okay? Which is the other type of list I'm going to learn. Okay? No, sorry, we are going to learn. So let's go ahead and import this. And it's a list, so it works the exact same. So while it's built underneath the same, while it's underneath, it's built differently. The commands are all exactly the same. But let's run this now. It was adding all the stuff to the beginning, no trouble. No trouble adding stuff to the beginning in a linked list. Linked lists are just like I increase by factor 2. So, should take 4 seconds to do, but I've still 5 seconds, so the other one still going. This would take 10 times longer, but whatever. So knowing which data structure to use based on your use case really makes a difference, right? With the array list, it took forever adding to the front. With the linked list, it's actually a linear time relationship again, adding it to the front, just because of the way we'll learn a linked list works. Okay. So before you go, I want to leave you with an example. Let's go ahead and look through our code an example of a constant time operation. Okay. So what is a constant time operation? It says this O of 1 time. And again, we'll get into what this means more on Monday. But a constant time operation says that doesn't matter how big the freaking thing is. It's going to take the same amount of time to run. And a great example of this is public int size, right? This returns the size of the list. It doesn't matter how big the size of the list is. That's just kept track of as a variable. So I just return the variable, right? Doesn't matter how big it's, and big numbers, small numbers, doesn't matter. Negative numbers, they all take up 4 bytes if they're integers. So returning a 4 bytes that represent a small number and 4 bytes that represent a large number doesn't really matter what size it was, right? Just that will take the same amount of time. Same with is empty. That's also constant time. Why? Because checking to see if, this is just 2 operations. I retrieve the size and then I compare it to 0. That's 0. That's 2 operations, sure. So maybe a bit slower than this one, but that's 1 command slower than this one, but it doesn't matter how fast, it's not dependent on the size. It's just not dependent on how big this is, right? It doesn't matter if we're dealing with a list of 100 or a list of 1,000,000. It's going to take the same amount of time regardless. Okay, so that's where I'll leave you with this. On Monday, we'll get more into this stuff. You're